Turn on the tap, and out comes safe water, ready to drink and use. It's the goal of every water utility, and filtration is just one of the treatment processes helping utilities reach that goal. The concept of filtration isn't new. Water filtering, including methods using sand and charcoal, are found as far back as 4000 BC in Greece and India. Ancient Egyptian pictographs even show the use of a filtration device. The first successful practice of water filtration in the U.S. involved the use of slow sand filters, where raw water was applied directly to large sand beds. These filters, however, weren't ideal for waters with high turbidity. Near the beginning of the 20th century, a water chemist named George Fuller distinguished himself through innovative new engineering ideas, advancing water treatment and public health. Fuller enhanced the workings of slow sand filtration by adding pre-treatment coagulants, clarification, and championing the concept of rapid sand filtration, one of several filtration processes that will be covered in this video. Engineered filtration of surface water mimics this process, passing water through sand and granulated media to remove suspended solids and other particles. Turbidity is the measurement used to gauge the concentration of these particles. Turbidity can cause aesthetic problems, resulting in customer complaints and lower consumer confidence. Some of the particles in the water can also shield some of the waterborne pathogens from disinfectants. Except in the case of cryptosporidium, filtration is the barrier for most surface water systems. High turbidity can also contribute to water quality problems in the distribution system. For these reasons, filtration is used on nearly all surface water, as well as groundwater that's determined to be under the direct influence of surface water. The filtration process works in two ways: mechanical straining and absorption. With mechanical straining, particles become trapped in the spaces between filter particles and are not able to continue downward. Adsorption is a chemical process that causes smaller particles to stick to individual grains of filter media or other particles. Adsorption is sometimes aided by the use of coagulation chemicals like alum. Alum is the common name for aluminum sulfate. When used, it causes particles in the water to stick together to form larger particles, or flock, making them easier to remove. Filtration can be used either as a part of conventional treatment or in a process called direct filtration. In conventional treatment, filtration usually occurs following coagulation, flocculation, and sedimentation. During coagulation, flocculation, and sedimentation, large particles or flock are settled out and removed from the water. Filtration then removes any remaining flock and smaller particles. Direct filtration is used following coagulation. This process reduces the number of treatment barriers in place to remove pathogens and results in more work for a filter. Direct filtration is only recommended for groundwater and surface waters with low turbidity. Direct filtration is most effective when it occurs immediately after coagulant chemicals are added and particles become sticky. Proper timing and careful monitoring are required. The filtration process used depends on the quality of the source water, system demand, and the types of contaminants that need to be removed. The most common method of filtration used by water utilities is gravity filtration. Filters are fed from the top and use gravity to maintain the flow of water through the filter media. The filtered water, or effluent, is collected at the bottom of the filter. Gravity filters can use various types of media and are classified as slow sand, rapid sand, high rate, and deep bed monomedia. Slow sand filters are the oldest type of filters used for water treatment in the United States. The media used is a layer of fine sand about 3.5 feet thick over graded gravel. Water is fed directly to the filter without any chemicals being applied. As raw water is fed, a sticky, skin-like layer forms at the top of the filter. This layer of biofilm is called a Schmutzsticke. The Schmutzsticke is made up of removed solids and biological growth, making the filter biologically active. Microorganisms in the biofilm help break down the organic material removed from the raw water. To clean a slow sand filter, an operator removes the top layer of sand manually, removing the smutsticka. The filter must then be conditioned by filtering to waste until a new smutsticka forms. Because this can take up to 2 days, slow sand filter systems either require extra finished water storage or multiple filters. Slow sand filters clog easily and are not recommended for use with turbidities above 10 NTU. They also filter at a slow rate and require a large footprint. A capacity of 1 million gallons per day can require up to 1 acre of filter bed. However, slow sand filters have low construction, operation, and maintenance costs and can be operated with little technology or instrumentation, making them a good solution for small systems. A more complicated but much faster method is rapid sand filtration. Rapid sand filters operate up to 40 times faster than slow sand filters, but require a higher level of monitoring and control. Rapid sand filters aren't as deep as slow sand filters. They consist of a 6 to 18-inch bed of gravel covered with a 2.5-foot layer of sand. Rapid sand filters have no smutsticka. Rapid sand filters are more efficient than slow sand filters, but still require a larger footprint than more modern systems. For even more efficient filtration and higher flow rates within a smaller footprint, many utilities use high-rate filters. These filters use layered media and can produce up to 4 times the flow rates as rapid sand filters. There are several types of high-rate filters: dual media, multimedia, and deep bed monomedia. Dual media filters consist of a bed of sand covered with a layer of granulated anthracite coal. Multimedia filters are similar to dual media but use 3 or more types of material. The most common configuration is a layer of garnet sand on bottom, silica sand in the middle, and coarse anthracite on top. In both dual and multimedia filters, different types of media are layered on top of one another. Generally, the larger the particles of a media, the lower it will be located in the filter. Gravel, which forms the base of most filters, stays at the bottom because it is larger and heavier than the sand on top. And the higher you go in the filter, the smaller the particles will become, with the exception of anthracite, which is found at the top. Anthracite has a lower weight per volume ratio or specific gravity, so it's able to sit on top of the smaller but denser sand particles below. Some mixing does occur at the interface level, but different media types generally remain stratified. The coarse anthracite layer at the top removes most of the suspended particles. What passes through is removed by the lower layers of media. The result is more of the filter depth is utilized for particle removal. Another high-rate filter used by water utilities is the deep bed monomedia filter. These filters use a single media, usually sand or anthracite, from 48 to 72 inches deep. The filter bed must be deeper than a conventional filter because the media is coarser. Monomedia filters can be operated at higher rates than dual media filters and are well suited for use with direct filtration systems. There are also several alternative approaches to filtration, including package treatment plants and biological filtration. Package treatment plants are small prefabricated units that are assembled at a factory and delivered in skid-mounted units. Package treatment plants can include a variety of treatment technologies, but generally consist of a coagulation flocculation unit, a sedimentation or coarse roughing filter unit, and a multimedia or pressure filter. These units are a good solution for small water utilities that require more complex treatment but lack the resources to design or construct traditional treatment facilities. Another process that continues to gain popularity is biological filtration. This process allows a biological growth to occur within the filter media. The microbes then break down biodegradable organic carbon, reducing taste and odor compounds and disinfection byproducts. Biological filtration is generally paired with ozone disinfection. Using chlorine up front can cause disinfection byproducts to form and inhibit biological growth. It's better to let the microbes grow and remove organic material in the water. The water can then go on to be chlorinated later in the process without disrupting the biological activity. Filter media may differ slightly from plant to plant, but most gravity filters require the same equipment to operate. Filter tanks are usually made of concrete and constructed side by side in filter galleries to minimize required infrastructure. Piping is required, however, to feed raw or pre-treated water to the filters, collect filter effluent, and feed and collect backwash water. A variety of under-drain systems are available to allow filtered water to pass through while retaining media in the filter bed. Wash water troughs are placed above the filter media to collect backwash water and carry it to waste. Most filters also require a surface agitation or air scour system to help release matter trapped in the upper layers of filter media and aid in the backwash process. To monitor filter performance and water quality, several types of instruments are used. Rate of flow controllers maintain a constant flow through the filter. Loss of head indicators help determine when a backwash is needed. Online turbidimeters or particle counters to monitor water quality, and streaming current monitors, filterability tests, and zeta potential tests all monitor the coagulation process. The amount of instrumentation required depends on the type of filter used. Slow sand filters require very little instrumentation, while more advanced filters are more dependent on precise monitoring and control. Regardless of the technology used, basic operating principles are the same for most systems. Conventional and direct filtration use a series of three processes: filtering, backwashing, and filtering to waste. During filtering, water is fed to the filter bed to maintain a depth of 4 to 5 feet over the media. As the filter run progresses, suspended material accumulates within the filter media. The more material a filter accumulates, the less efficiently it is able to filter. There are two ways to operate a filter while accounting for this decrease in capacity over time. The first is called controlled rate of flow. A modulating control valve on the effluent discharge is used to maintain a constant flow rate through the filter. At the start of the filter run, water flows through the media easier, so the valve is only partially open. As the filter clogs, water moves more slowly through the media and the valve is gradually opened to compensate. Another control process is called variable declining rate filtration. This method allows the flow rate to slowly decrease as the filter gets dirty. Think of a filter not as a particle removal device, but a particle storage device. During filter runs, particles will attach and detach from the filter media, and eventually they'll either start to come through the bottom of the filter or the filter will get clogged. Once clogged, the filter must be taken out of service for cleaning. This process is called a backwash. There are three factors to consider in determining when to backwash. The first is head loss. This is the difference in pressure between the top of the filter and where the water exits to the underdrains. Head loss indicates that the filter is clogged with material and can no longer maintain effective flow rates. When head loss reaches a predetermined level, usually about 8 feet, a backwash must occur. This is called terminal head loss. The second indicator for a backwash is an increase in filtered water turbidity. As the filter accumulates material, flock and particles begin to break through the filter, raising turbidity in the finished water. The third indicator that a backwash is needed is the length of the filter run. Some plants set a time limit for filter runs and then backwash once that limit is reached, whether it's needed or not. Depending on the plant and type of filter, one indicator may be more useful than the others. But it's important to consider all three. If any of these criteria are met, it's time for a backwash. In simple terms, this means running filtered or finished water through a filter in reverse at a high velocity to loosen and remove accumulated material. If a filter normally runs at 3 or 4 gallons a minute per square foot, it may backwash at 18 to 20 gallons per minute per square foot. The combination of reversing flow and increasing velocity lifts and removes the particles from the filter. To start the backwash, the filter is drained to within 6 inches of the top of the media, and a high-rate wash with surface washers or an air scour are turned on for 1 to 2 minutes. This helps break up any surface layers of filtered material. Next, the backwash valve is partially opened to expand the bed. This agitates the top portion of the media and helps break up and release suspended solids. After a few minutes, the backwash valve is further opened until the bed has expanded 20 to 30%. If surface washers are used, this allows them to scrub the interface, the area between the anthracite and sand layers. The auxiliary wash and air scour should be stopped before the water rises to the bottom of the wash water troughs to reduce media loss. Once the backwash water starts running clear, a low-rate wash continues to allow the media to re-stratify into layers. This takes a couple minutes. The backwash valve is then closed and the filter is clean. Following a backwash, the filter is put back into operation. However, the filtered water is sent to waste rather than the clear well. The backwash process isn't 100% efficient. There may still be some particles stuck in the media. Therefore, the first bit of water coming out of the filter may have a higher than normal turbidity level. So, following a backwash, filtered water is sent to waste until the turbidity drops to an acceptable level. The time it takes to return to normal filter operation is called filter ripening time. Operators will want to measure what that time is for future reference and to explore ways to minimize the filter-to-waste time. Possible ways to do that could include adding coagulant to the back end of the backwash to condition the media, or adding filter aids ahead of the filter to make the water more filterable. It's one of the most basic processes in water treatment, but proper filtration requires careful monitoring and control. When not properly maintained, a filter can cause all sorts of problems, but combined with proper chemical treatment, filtration is an indispensable tool for water treatment.